What if I told you that the most severe threat to global civilization is not a war, not a pandemic, not a slowly rising sea level, but a star that has already demonstrated, in the chemical memory of ancient trees, that it is capable of erasing modern infrastructure in a single afternoon? In May 2024, Florida saw aurora for the first time in 500 years. It was the strongest geomagnetic storm in 2 decades. It was also, by the standards of what our sun has actually done before, a minor event. What came before it, preserved in isotopes and ice, is something else entirely. Stay with me to the end tonight, because the solar storm that could end the modern world is not theoretical. It is just late. The science is confirmed. The risk is real. And the gap between what the sun is capable of and what the world has built to survive it is wide enough to matter to every person alive today. Hit subscribe and follow along, because this is not a story with a comfortable ending yet, and the only way that changes is if enough people understand what is actually at stake. We are not done asking questions, and neither, it turns out, is our star. Part 1. The night. The sky turned wrong. Something happened in May 2024 that most people filed away as beautiful, and almost nobody understood as a warning. On the evening of May 10th, people in Florida stepped outside and looked up. The sky was doing something it had no business doing that far south. Ribbons of green and red light were rippling across the atmosphere, dancing above palm trees and swimming pools and shopping centres. People pulled out their phones. They posted the videos. The comments were full of heart emojis and exclamation points. In Hawaii, the same thing was happening. In Jamaica, people were standing in their yards, looking up at lights that their great-great-great-grandparents had never seen, that no living person in those places had ever seen, that no human being in those latitudes had witnessed in roughly 500 years. That is not a poetic exaggeration. That is the scientific assessment. The last time auroras were reliably documented that far toward the equator was sometime in the 1500s, during a period of extreme solar activity. And here they were again, glowing quietly above the tropics, while people uploaded them to social media with captions like "What a magical night." It was not a magical night. It was a warning flare from a star that has been trying to get our attention for a very long time. The National Oceanic and Atmospheric Administration, the agency responsible for space weather forecasting in the United States, classified the May 2024 event as a G5 geomagnetic storm. G5 is the top of the scale. It is the category reserved for the most extreme geomagnetic disturbances Earth can experience. The last time NOAA recorded a G5 was in October 2003, during what became known as the Halloween storms. Before that, you have to go back to the 1989 Quebec event, which we will get to shortly. G5 storms are not supposed to be common. They are supposed to be rare, serious, and treated accordingly. The instruments that monitor Earth's magnetic field registered readings that had not appeared in the modern data record. Magnetometers around the world were spiking in ways that made operators double-check their equipment. For a few hours, the sun was effectively punching Earth's magnetic field like a fist hitting a stretched piece of fabric, over and over, compressing it, distorting it, sending enormous electrical currents cascading down through the upper atmosphere and into the ground below. Up in orbit, the situation was considerably less scenic. Roughly half of all active satellites in low Earth orbit had to fire their thrusters to counteract the increased atmospheric drag. When a geomagnetic storm heats Earth's upper atmosphere, that atmosphere expands outward. Satellites that were previously flying through near vacuums suddenly found themselves moving through air that was just thick enough to slow them down, pulling them toward re-entry. Some SpaceX Starlink satellites were lost entirely. They could not compensate fast enough. They fell. On the ground, inside power utilities across North America, something was happening that did not make the evening news. Engineers were watching their system with the particular kind of focused attention that precedes very bad outcomes. Internal assessments were being shared between grid operators with language that was, by the standards of engineering communications, alarming. The grid had come close. How close is a matter of ongoing professional debate, but the phrase "within inches of widespread failure" appeared in multiple private assessments reviewed by researchers afterward. The headlines the next morning were mostly about the pretty lights. Here is how a geomagnetic storm actually works, because the mechanics matter for everything that comes next. The Sun is not a stable, quiet object. It is a churning ball of plasma, constantly generating magnetic fields that twist and tangle and sometimes snap. When those magnetic field lines break and reconnect, they release enormous amounts of energy. Sometimes that energy is released as a flash of X-ray radiation, which we call a solar flare. Sometimes it also launches a massive bubble of magnetized plasma outward from the Sun's surface, which we call a coronal mass ejection, or CME. When that bubble of plasma is aimed at Earth and arrives here, it collides with Earth's own magnetic field, and the interaction produces geomagnetically induced currents, basically extra electricity running through anything conductive near the surface of the planet. Power lines, pipelines, communication cables, transformers. The May 2024 storm was produced by a sunspot region of unusual complexity. It fired multiple CMEs in quick succession, and those CMEs arrived at Earth in a coordinated way that amplified their combined effect. Scientists were surprised. Not panicked, but genuinely surprised. Because this level of activity was not supposed to be happening yet, or at this intensity. Here is where the surprise becomes significant. Scientists had predicted that solar cycle 25, the current solar cycle which began around 2019, would be a weak one. Not dangerous, not dramatic, probably below average. That was the consensus forecast from multiple independent modelling groups. They were wrong by a substantial margin. By early 2025, the cycle's peak sunspot number was running roughly 40% above the highest predictions, and the Sun kept going. In early 2026, a sunspot region designated 4366 produced a sustained series of powerful flares, including multiple M-class events and an X8.3 flare in February 2026, one of the strongest flares recorded in years. Radio blackouts were reported across multiple continents. Satellite operators went back on high alert. The experts who model solar activity were caught off guard. Not catastrophically, not embarrassingly, but measurably and meaningfully off guard. And if the models failed to predict a routine solar cycle, a pattern of behaviour that happens every 11 years and has been observed for centuries, then what does that say about our ability to predict something far rarer and far more powerful? Because it turns out the tree rings have something to say about that, and what they say should probably make you uncomfortable. The evidence is old, it is quietly confirmed by mainstream science, and almost nobody outside of a small community of researchers is taking it seriously enough. The story of what the trees know begins with an isotope, a discovery, and a woman named Miyake. And what she found in 2012 changed the way a handful of scientists think about the Sun, and should have changed the way everyone else does too. Part 2, what the trees remember. There is a way of reading the past that does not involve written records or human memory. It is encoded in the rings of ancient trees, in the bubbles of trapped air inside polar ice, and it goes back tens of thousands of years before anyone was paying attention to the sky in any systematic way. And when scientists learned how to read this record carefully enough, they found something that nobody had put there intentionally, a series of sudden spikes in a particular chemical signature that could only mean one thing. Carbon-14 is a radioactive isotope of carbon. It is produced when cosmic rays, which are high-energy particles streaming in from space, collide with nitrogen atoms in Earth's upper atmosphere. Under normal conditions, the rate of carbon-14 production is relatively stable, and because living trees absorb carbon from the atmosphere as they grow, each annual ring in a tree trunk contains a preserved sample of the atmospheric carbon-14 from that specific year. It is, in effect, a chemical diary that the tree writes without knowing it is writing anything. Beryllium-10 works similarly. It also forms when cosmic rays interact with the atmosphere, and it gets deposited into polar ice, where it is preserved in annual layers. Two independent chemical records written by two different processes, archived in two completely different materials, both measuring the same thing: how much high-energy particle radiation was hitting Earth's atmosphere in any given year. When Miyake, a researcher at Nagoya University in Japan, analysed tree ring records from that year in 2012, she found something that should not have been there. In the rings corresponding to 774 and 775 CE, there was a sudden enormous spike in carbon-14. Not a gradual increase, not a slow drift upward, a sharp vertical jump in a single year, far larger than anything that normal variation in cosmic ray flux could explain. When the Beryllium 10 record from ice cores was checked for the same period, it showed the same spike. Both records, independently, were screaming the same thing. Something hit Earth in 774 or 775 CE with a burst of high-energy particles unlike anything in the modern instrumental record. Miyake's paper was published, noted by specialists, and largely ignored by the wider world. Then, as researchers began looking more carefully at the tree ring record, a second spike appeared, 993 to 994 CE. Same signature, same sudden jump, same independent confirmation from ice cores. Then researchers started going further back and further, and the picture became considerably more unsettling. These events are now called Miyake events, and they represent something that the standard framework of solar activity had not really accounted for. The possibility that the sun occasionally produces particle storms of a completely different magnitude than anything we have measured with modern instruments. Everything in our scientific understanding of solar risk, every model, every grid protection standard, every satellite design specification is based on the instrumental record, and the instrumental record goes back, at best, 150 years. What the tree rings are showing us extends back over 14,000 years, and in that longer record the sun looks considerably more dangerous. The largest Miyake event yet identified occurred approximately 14,300 years ago. When researchers applied updated modelling to the isotope data from this event, the results were striking. The particle flux from this event was estimated to be more than 500 times stronger than the largest solar particle events recorded in the modern era. 500 times. For comparison, the May 2024 G5 storm was already the strongest geomagnetic event in 2 decades. Now imagine something 500 times more energetic than the worst events we have modern data for. And this is where the analogy breaks down, because comparisons to known things become almost inadequate. If the Carrington event of 1859, the gold standard of historical solar disasters, was equivalent to a Category 5 hurricane, then a Miyake-class event is not a bigger hurricane. It is a different category of phenomenon entirely. It is a storm from a different scale of physics, running through the same infrastructure that struggles with the ordinary version. What makes Miyake events genuinely difficult to reason about is that they appear to have no predictable rhythm. The known events cluster at 775 CE, 993 CE, and the distant prehistoric spike 14,300 years ago, along with a small number of other candidate events at various points in between. There is no obvious periodicity. There is no 11-year cycle, no grand solar minimum pattern, no astronomical alignment that predicts them. They arrive without warning in the record, persist for 1 to 3 years in the isotope signal, and then the record goes quiet again. Here is the part that rarely gets mentioned in the occasional news coverage these discoveries receive. Only about 16% of the available tree ring record has been analysed with sufficient resolution to detect Miyake events. 16%. The rest of the record is either unanalysed, sampled at too coarse a resolution to detect a single-year spike, or simply has not been processed yet, which means the number of known Miyake events is almost certainly a significant undercount of how many have actually occurred. Think about what that means statistically. If the known events represent a rough lower bound on frequency, and the actual number could be substantially higher, then the recurrence interval we might naively estimate from the known events is probably too long. These things may happen more often than the current data suggests. We do not know, and that uncertainty is not a gap in fringe speculation. It is a gap in peer-reviewed science that the researchers themselves acknowledge openly. The particles involved in a Miyake event are not the same as the charged plasma of a typical CME. Solar energetic particles produced in extreme events are accelerated to relativistic speeds, a significant fraction of the speed of light, by shock fronts in the solar corona. They penetrate deeper into Earth's magnetic field. They reach lower altitudes in the atmosphere. In the most extreme cases, they produce what scientists call a ground-level enhancement, a moment when the particle flux becomes detectable, not just in space or the upper atmosphere, but at Earth's surface, with ordinary radiation detectors. The 775 event was almost certainly a ground-level enhancement, something that's strong, arriving today, would not just disrupt satellites and power grids, it would penetrate spacecraft shielding. It would deliver radiation doses to astronauts that would be medically serious within hours. And for infrastructure on the ground, the geomagnetically induced currents produced by the associated magnetic storm would be in a range that existing protection standards were not designed to handle. The scientists who study this are not alarmists. They publish careful, methodical papers in peer-reviewed journals. They note their uncertainties. They acknowledge what they do not know. But when you read between the lines of their academic language, a consistent message emerges. The modern world has never experienced an event like this. The infrastructure that runs modern civilization was designed around a threat envelope defined by about 150 years of instrumental data, and the tree rings are telling us that envelope is incomplete by orders of magnitude. The question is not whether another Miyake event will happen. In geological and astronomical terms, they are a known feature of solar behaviour. The question is when. And on that question, the trees are silent. They only show us the aftermath. What they cannot tell us is what was happening on the Sun in the weeks and months before each of these events, whether there were warning signs, whether a civilization equipped with modern sensors could have seen it coming. That question leads us somewhere uncomfortable, because it turns out we're not particularly good at predicting even the routine behaviour of our own star. Part 3. The Sun that laughed at our models. Prediction is a form of confidence. When scientists publish a forecast, they are saying, in effect, we understand this system well enough to tell you what it will do next. And for decades, solar scientists had a reasonable track record. Not perfect, but reasonable enough to feel calibrated. Then solar cycle 25 began, and the Sun decided to make its feelings about our confidence quite clear. Every 11 years, roughly, the Sun goes through a cycle of magnetic activity. Sunspot numbers rise from a quiet minimum to a turbulent maximum and then fall again. This has been observed and documented since the 1700s. We have data on more than 24 complete solar cycles. We have physics models, statistical models, machine learning models, and panel after panel of expert consensus forecasts. Solar cycle prediction is one of the more established subfields of space weather science. Before solar cycle 25 began, NOAA convened a panel of experts to produce an official prediction. The panel forecast a weak to moderate cycle, with a predicted peak sunspot number somewhere around 115. Some models went lower. This was not a rogue minority view. It was the scientific consensus, published officially, used by satellite operators and grid planners to calibrate their risk assessments for the coming decade. By 2024, the actual peak sunspot numbers were running at approximately 160 to 170, not slightly above the forecast, significantly above it. About 40% higher than predicted, which in practical terms meant a meaningfully more active Sun producing more frequent and more intense events than the infrastructure community had been told to plan for. The May 2024 G5 storm arrived in a cycle that was supposed to be quiet. It was not the last surprise. Understanding why the models failed requires a brief detour into what sunspots actually are. A sunspot is a region on the Sun's surface where intense magnetic field lines break through, suppressing the convective circulation of hot plasma and creating a cooler, darker patch. They are visible in ordinary filtered telescopes and have been counted systematically for centuries. Their number is used as a proxy for the Sun's overall magnetic activity level, because more sunspots generally mean more flares, more CMEs, and more energetic particle events. The sunspot number is, in other words, the key input to almost every operational space weather forecast. But the physical mechanism that drives the sunspot cycle, the solar dynamo operating in the Sun's interior, is genuinely poorly understood. It involves the interaction of rotation, convection, and magnetic field in a plasma that we cannot directly observe. We see only the surface expression of processes happening thousands of kilometers below. The models are built on incomplete physics, calibrated against a historical record that covers a few dozen cycles, applied to a system that operates on timescales ranging from seconds to millions of years. When the actual behavior diverges from the model, scientists update their understanding. That is science working as intended. But here is what that process reveals. Even for an 11-year cycle that has been running, as far as we know, for billions of years, our predictive capability is limited enough to miss the peak by 40%. This is not a criticism of the scientists involved. It is a statement about the fundamental difficulty of the problem. Now take that uncertainty and apply it to Miyake events. These are not part of any observed cycle. they do not appear to be driven by sunspot maxima, since the 775 CE event may not have occurred during a particularly active period of the normal solar cycle. They seem to emerge from some combination of conditions that the standard models do not capture, and may not even include the right variables to capture. If we struggle to predict routine solar cycles, the probability of successfully forecasting a Miyake-class event approaches something that is, scientifically speaking, very close to zero. The implications run in two directions. The first is practical. Grid operators, satellite manufacturers, and government agencies use solar cycle forecasts to make risk management decisions. If those forecasts systematically underestimate activity, then risk management decisions are systematically miscalibrated. The infrastructure is being designed and maintained against a threat level that is lower than what the Sun is actually capable of delivering on any given cycle. The second implication is epistemological, and it is subtler, but perhaps more important. When experts predict something confidently and the outcome diverges substantially, there is a well-documented human tendency toward one of two unhealthy responses. The first is to dismiss the experts entirely. The second, and arguably more dangerous one, is to assume that the failure was an anomaly, absorb the lesson superficially, and continue with essentially the same level of confidence in the next forecast. Both responses lead to poor outcomes. What is needed instead is a genuine recalibration of uncertainty, a willingness to say, we do not know as much as we thought we did, and our planning should reflect that. There is also a more personal dimension to the prediction failure. Scientists are human beings operating within institutions, funding structures, and professional cultures that reward confident claims and penalize excessive hedging. Publishing a forecast that says anything could happen is not career advancing. Publishing a precise number, even one that turns out to be wrong, demonstrates methodological rigor and expertise. This is not a conspiracy. It is an ordinary feature of how expert communities function under institutional pressure, but it means that the public confidence conveyed by official forecasts may consistently exceed the genuine epistemic confidence that exists inside the field. When the scientists who study Miyake events discuss prediction, their language becomes notably careful. They do not say these events are unpredictable in principle, because they do not know that. But they say, consistently, that no known precursor signal has been identified that would distinguish an ordinary solar maximum from one that produces a Miyake-class event. The isotope spikes appear suddenly, without any escalating signature in the preceding years of the record. The record just goes from normal to catastrophic in the space of a single annual layer. Which brings us back to the question of near misses, because the near misses are the part of this story that should change how everyone thinks about probability. Part 4. The miss that should have ended everything. 9 days. The margin between the modern world and a catastrophe of a scale that has never occurred in the industrial era was 9 days. The event is real, it is documented, and it is not nearly as well known as it should be. In July 2012, a coronal mass ejection of exceptional power left the Sun. The ejection was associated with a sunspot region that had been producing elevated activity, and the CME it launched was fast, the plasma was dense, and the magnetic field orientation was configured in precisely the worst way possible for Earth's magnetosphere. Scientists who later analysed the event estimated its strength as comparable to, and possibly exceeding, the 1859 Carrington event, which remains the most powerful solar storm in the historical instrumental record. The Carrington event knocked out telegraph systems across North America and Europe. Operators received electric shocks from their equipment. Some telegraph lines continued to transmit messages even after being disconnected from their power sources, running entirely on the current induced by the geomagnetic disturbance. In 1859, the telegraph was the most advanced communications infrastructure on the planet, and a solar storm that is, by modern estimates, less energetic than what Miyake events can produce, temporarily destroyed it. The July 2012 CME did not hit Earth. It left the Sun when the relevant sunspot region was pointed roughly 90 degrees away from us, and the plasma cloud travelled out into interplanetary space and passed by harmlessly. Earth was not in the firing line. 9 days earlier in the Sun's rotation, and that sunspot region would have been pointed directly at us. A subsequent study published in the journal Space Weather, authored by a team including physicists from the University of California, estimated that the probability of a Carrington-class CME hitting Earth in any given decade is somewhere between 10 and 12%. That is not an unlikely event in the way that, say, an asteroid impact is unlikely. 10 to 12% per decade means that over the course of a typical human lifetime, the expected number of Carrington-class events aimed at Earth is greater than 1. We have simply been fortunate that the most powerful recent examples have been misdirected. The reason the July 2012 near miss matters beyond its own drama is that it serves as a calibration point for how the modern grid would respond to a Carrington-scale event. Researchers who have run the numbers do not come to reassuring conclusions. The power grid that exists today is vastly more interconnected and vastly more dependent on transformers that were not designed with geomagnetic threats in mind than anything that existed in 1859. The same physics that would induce currents in telegraph lines in the 1800s would, in the 21st century, induce those currents in high-voltage transmission lines thousands of kilometers long, feeding into extra high-voltage transformers that cost between $3 and $10 million each, that take 1 to 3 years to manufacture, and that essentially no country maintains in meaningful reserve stockpiles. The geomagnetically induced currents, or GICs, produced by a severe storm do not necessarily destroy transformers instantly. They saturate the transformer's core with direct current, which the transformer is not designed to handle, causing it to overheat. Depending on the severity and duration of the GIC exposure, transformers can fail hours or days after the storm event itself, complicating any emergency response, and failed extra high voltage transformers cannot be repaired in the field. They must be replaced by components that do not exist in warehouses anywhere. The 1989 Quebec blackout is the most useful modern reference point. On March 13, 1989, a geomagnetic storm rated well below G5 intensity hit Earth. Within 90 seconds of the storm's arrival, the entire Hydro-Quebec power grid collapsed. 6 million people lost electricity for up to 9 hours. The Quebec event was a moderate storm by the standards of what the sun can produce, and it caused a grid failure that affected a significant portion of a major industrialized province for most of a day. Now consider that a Carrington-class event is estimated to be 10 to 20 times more energetically intense than the 1989 storm, and a Miyake-class event is potentially hundreds of times beyond that. The Quebec blackout extended to cover most of a continent, lasting not 9 hours but potentially months, with transformers that cannot be replaced in any reasonable time frame. That is the scenario that runs through the models of researchers who study this problem seriously. There are also subtler solar phenomena that the popular coverage of space weather mostly misses. Coronal holes, regions of the sun's surface where the magnetic field opens outward and allows solar wind to escape at higher speeds, can produce sustained geomagnetic disturbances that are less dramatic than a CME but persistent enough to cause cumulative stress on satellite electronics and power systems. The equinox effect, a documented phenomenon where geomagnetic storms are statistically more intense in March and September due to the alignment geometry of Earth's magnetic field with the solar wind, means that spring and autumn storms consistently punch above their weight. In March 2025, an R3 level radio blackout event was recorded when a powerful flare disrupted high-frequency communications across multiple continents. In early 2026, the X8.3 flare from Sunspot region 4366 produced radio blackouts that affected aviation communications and GPS precision over a significant portion of the sunlit hemisphere. These are not civilization-ending events. They are reminders that the sun is doing this all the time, at the level of nuisance and manageable disruption, and occasionally escalating without warning to something considerably more serious. The disturbing possibility that some researchers raise is that there may be no reliable warning signal that distinguishes a routine active period from one that is about to produce an extreme event. You cannot look at the sun today and know whether a Miyake-class event is hours away or 10,000 years away. The precursor signatures, if they exist, have not been identified, and yet the decisions about how much protection to invest in, how seriously to treat the risk, how urgently to act, are being made right now, on every day when nothing terrible happens and the urgency feels theoretical. The infrastructure that would fail is not theoretical, and what it looks like under extreme stress is the subject we need to confront directly. Part 5. The grid, the satellites, and the long dark. Imagine a Tuesday afternoon. Nothing unusual about the sun. A flare begins. In 8 minutes, the X-ray radiation from that flare reaches Earth, causing immediate radio blackouts on the sunlit side of the planet. High-frequency aviation communications go dark. GPS receivers begin producing location errors. 12 to 24 hours later, depending on the CME's speed, the plasma cloud arrives, and then the real problem begins. Modern power grids are extraordinary achievements of engineering. They balance supply and demand in real time across vast areas, routing electricity through a network of generation facilities, transmission lines, substations, and transformers with a precision that most users never think about. This complexity is also a vulnerability. A geomagnetically induced current doesn't need to take down the whole grid at once. It only needs to damage the right transformers in the right places, and the cascading consequences do the rest. Extra high voltage transformers, the massive units that step voltage up and down for long-distance transmission, are the critical choke points. These are not off-the-shelf items. They are custom-engineered pieces of equipment, often built specifically for a particular location in the grid, weighing hundreds of tons, requiring specialized installation and testing. The largest ones are manufactured by a small number of factories globally, most of them in Asia and Europe. The production queue for an extra high voltage transformer in normal times is 12 to 24 months. In a scenario where multiple transformers fail simultaneously across a continent, there is no queue. There is a waiting list that would stretch beyond any reasonable emergency timeline. Lloyd's of London, not an institution known for catastrophism, published a detailed assessment in 2013 examining the consequences of a Carrington-class geomagnetic storm on the North American grid. Their estimate, between 20 and 40 million people could lose power for a period ranging from weeks to years. The economic loss they estimated ranged from $600 billion to $2.6 trillion, and that estimate was based on a Carrington-class event, not a Miyake-class one. The upper end of the scenario space was not included because it was, in the actuarial phrase, not well characterized enough to model. Satellites present a different vulnerability profile. The low Earth orbit environment where most operational satellites live, including communication satellites, Earth observation platforms, and the GPS constellation's operational spares, is sensitive to space weather in multiple ways. The atmospheric drag effect from solar heating can deorbit satellites that lack sufficient propulsion to compensate. High-energy particle radiation can damage solar panels, reducing power generation. Radiation can induce bit flips in computer memory and corrupt software states in ways that may not be immediately apparent. Charged particle radiation can permanently damage sensitive sensor arrays. The GPS constellation itself is a particular concern. Global positioning infrastructure is so thoroughly integrated into modern logistics, financial transactions, emergency services and military operations that disruption to GPS would not be experienced as a GPS problem. It would be experienced as everything going slightly wrong at once, in ways that would take hours or days to diagnose. Financial trading systems that use GPS timestamps for transaction ordering. Agricultural machinery that uses GPS for autonomous operation during planting and harvest. Air traffic control systems, emergency dispatch routing. The effects would propagate through systems whose operators may not immediately recognize the space weather connection. Aviation communications represent another underappreciated vulnerability. High-frequency radio, the backbone of communications for flights over oceans where there is no radar or ground-based radio coverage, is highly susceptible to ionospheric disturbance. During strong solar flares, HF communications can black out for hours. During a sustained extreme event, they could be unreliable for days. Transatlantic and trans-Pacific aviation would face extended periods where pilots cannot communicate with air traffic control through normal channels. Undersea communication cables, the fiber optic infrastructure that carries something like 95% of all international internet traffic, have a lesser-known vulnerability to geomagnetic storms. The cables span thousands of kilometers and contain electrical amplifier repeaters at regular intervals that require power. Those repeaters are connected to onshore power systems at the cable endpoints. A geomagnetic storm that induces large currents through the Earth's crust can damage the shore-end equipment and the electronic components in the repeaters. In a scenario where multiple cable systems experience simultaneous problems, internet traffic between continents could be reduced to satellite-based fallback systems with a fraction of the capacity. The water and sanitation systems that modern cities depend on are heavily automated and electrically powered. Modern hospitals run on complex electronic systems for patient monitoring, medication management, and life support. Supply chains depend on real-time logistics software running on servers that require continuous power. None of these systems were designed with a multi-week grid failure in mind, because that scenario was considered implausible. There is a way to make the infrastructure argument feel abstract, and that is by talking about systems and assets and economic losses. There is also a more direct way. In a scenario where major portions of the North American or European grid fail for an extended period in winter, the mortality consequences are not mainly economic. They are not primarily about lost productivity or property damage. They are about hospitals running out of generator fuel. They are about water treatment plants going offline. They are about elderly people in cold climates who cannot heat their homes. The people who study this risk for a living use careful, measured language. But when you ask them directly about the human cost of an unmitigated extreme solar event, the language gets quieter. The stark question is this: if a Miyake-class event arrived tomorrow, how much of the infrastructure that keeps several billion people alive would still be functioning at the end of the week? The honest answer, based on current protection standards and stockpile realities, is not enough. And the honest follow-up question is, what would it actually take to change that? Because it turns out the answer to that question is not as complicated as the silence around this topic might suggest. That answer, and the reasons it has not been implemented, take us somewhere darker and more interesting than the physics alone. Part 6. Into the physics of catastrophe. There is a spectrum of solar events, and most people who follow space weather news only ever hear about one end of it. The flares and CMEs that make headlines are the upper end of the routine, things that disrupt satellite operations and produce auroras and occasionally stress the power grid. They are remarkable, genuinely consequential events. But they occupy a different physical category than what produces a Miyake event, and understanding that difference requires going deeper into what happens near the Sun when an extreme event begins. A standard CME originates when tangled magnetic field lines in the solar corona suddenly snap and reconnect, releasing stored magnetic energy as kinetic energy in an ejected plasma bubble. The plasma moves outward at hundreds to thousands of kilometers per second. When it arrives at Earth, the geomagnetic effect is mostly from the magnetic structure of the CME interacting with Earth's magnetosphere. The charged particles in the CME are energetic, but their energy is in the range that Earth's magnetic field is reasonably effective at deflecting. Extreme solar energetic particle events, the kind associated with Miyake events, involve a different acceleration mechanism. When a fast CME drives a shockwave through the corona, that shock can accelerate ambient particles to a much higher energy range, approaching relativistic speeds. The distinction matters enormously for how those particles interact with everything they encounter. A particle travelling at a significant fraction of the speed of light does not behave the same way as one moving at a few hundred kilometers per second. It penetrates through things that slower particles cannot reach. Earth's magnetic field is, under normal circumstances, a remarkable piece of natural infrastructure. It deflects most of the solar wind around the planet, routing it along field lines toward the polar regions, where it produces auroras but causes limited damage to most of the world. The radiation belts, the Van Allen belts, serve as a second layer of protection, trapping energetic particles in stable orbits around Earth. During a severe geomagnetic storm, both of these protective systems are partially overwhelmed. The magnetopause, the outer boundary of Earth's magnetic field, is compressed inward by the enhanced solar wind pressure, exposing satellite orbits that are normally inside the magnetosphere to direct solar wind exposure. A ground-level enhancement, or GLE, is what happens when the particle energies are high enough to penetrate all the way to Earth's surface. These have been recorded during strong historical events, including the February 23, 1956 event, which remains the largest GLE in the instrumental record. During that event, cosmic ray monitors at ground level recorded particle flux increases of several thousand% above background. For context, the radiation dose delivered during even a relatively modest GLE is medically significant for people in aircraft at high altitudes, which is why aviation authorities have protocols for descending to lower altitudes during such events. For a Miyake-class event, The GLE component would be in a regime that existing instruments have never measured. Researchers working backward from the isotope signatures estimate that the particle flux from the 775 CE event would have been sufficient to produce ground-level enhancements sustained over hours, not minutes. The biological implications for unshielded individuals at altitude or in space during such an event would be serious. Astronauts on the International Space Station or in any near-Earth orbit would need to shelter in the most shielded compartments available and would still receive doses that exceed annual occupational exposure limits within hours. The radiation belt behavior during extreme events adds another dimension of complexity. During a large CME event, the outer Van Allen belt is often temporarily erased as its particle population is swept away by the disturbed solar wind, then rebuilt with a new population of injected particles as the storm subsides. During an extreme Miyake class event, the dynamics of this process are not well modelled. Some simulations suggest that the radiation belt reformation process after such an event could produce a temporarily enhanced radiation environment in low Earth orbit lasting weeks to months, during which satellite operations would face abnormally elevated radiation exposure throughout their orbits. The Sun has also produced phenomena that are less commonly discussed in public space weather coverage. Solar cosmic ray showers, in which extreme particle events create cascades of secondary particles in Earth's atmosphere, can affect the chemistry of the ozone layer. There is evidence in ice cores and atmospheric models that Miyake events of sufficient intensity may have caused brief but measurable depletions of stratospheric ozone, with implications for UV radiation reaching the surface. This is not in the mainstream public conversation about solar risk. It is in the scientific literature, noted carefully, and its significance is debated. But it represents a class of consequence that extends beyond the electrical and navigational systems usually discussed. One of the genuinely unsettling aspects of extreme solar physics is how many amplifying mechanisms might exist that are not yet understood. The known physics is already serious, but solar science is still a field with significant frontiers. The internal dynamics of the Sun that drive the most extreme events are not fully characterized. The coupling between different layers of the solar atmosphere during rapid energy release events has revealed surprising behaviors even in modern, well-observed events. And the interaction between Earth's magnetosphere, ionosphere, and ground-level electrical environment during extreme disturbances involves non-linear feedback processes that current models may not capture accurately. When the researchers who model the upper end of the solar event distribution are asked whether the isotope-based estimates of Miyake event intensity might be wrong, the honest answer is yes in both directions. The estimates could be too high if some of the isotopic signal has been amplified by terrestrial processes. They could also be too low if the most intense part of the event was shorter duration than the annual resolution of tree rings can capture. The uncertainty, in other words, does not only run in the reassuring direction. The question of whether there are unknown amplification mechanisms lurking in solar physics that could make even the Miyake event estimates look conservative is the kind of question that keeps some researchers up at night. Not because there is evidence for such mechanisms, but because the track record of solar science, particularly the recent track record of predicting solar cycle intensity, is not one that encourages complacency about the limits of current understanding. Part 7. Patterns, planets, and things we cannot quite dismiss. Science runs on mechanisms. A correlation without a mechanism is a curiosity at best and a delusion at worst. But correlations keep showing up in solar data, and the question of which ones represent real physics and which ones represent the human tendency to see patterns in noise is genuinely difficult to settle. Some of these correlations involve the planets. The idea that the orbital positions of the large outer planets, primarily Jupiter, Saturn, Uranus, and Neptune, might exert a tidal influence on the Sun sounds, at first like the kind of claim that belongs in an astrology column rather than a physics journal. The gravitational influence of Jupiter on the Sun is real and measurable, but it is tiny compared to the Sun's own self-gravity. The tidal forces involved are orders of magnitude smaller than any energy scale relevant to solar flares or CMEs, and yet, a persistent community of researchers has spent decades looking for correlations between planetary alignments and solar activity, and some of them find statistically suggestive patterns that are difficult to explain as pure noise. The mainstream solar physics community is skeptical, and for good reasons. The proposed physical mechanism, when advocates attempt to specify one, usually involves some form of tidal resonance inside the solar convection zone or in the tachocline, the boundary layer between the Sun's radiative interior and convective envelope. These mechanisms are not ruled out by first principles, but they require the Sun's interior to respond to extremely weak forcing in a highly nonlinear way that amplifies tiny tidal perturbations into observable effects on the surface. No convincing physical model of this process has been published and survived peer review. What keeps the debate alive is not the quality of the mechanism, it is the persistence of the correlations. Some analyses of sunspot records going back to the 1700s find periodicities that align with planetary orbital resonances, particularly with the roughly 20-year Jose cycle, which reflects the periodicity of Jupiter and Saturn's relative alignment. Other analyses find that the most severe historical geomagnetic events cluster around certain planetary configurations more than random chance would predict. When statistical tests are applied carefully, accounting for the number of ways one can slice the data, most of these correlations weaken or disappear, but not all of them. The honest position, which very few researchers in either camp adopt publicly, is that the question is not fully settled. The evidence for a real planetary influence is weak and contested. The evidence against it is primarily theoretical, based on the smallness of the proposed forces, rather than a definitive empirical demonstration of absence. In a field where the relevant physical processes occur thousands of kilometers beneath the surface of a star, theoretical arguments about what should and should not matter carry inherent uncertainty. What is better established is the existence of long solar cycles beyond the familiar 11-year Schwabe cycle. The Hale cycle runs about 22 years and represents the time for the Sun's magnetic polarity to complete a full reversal cycle. The Gleisberg cycle, approximately 80 to 90 years, appears in sunspot records and has been associated with periods of generally elevated or suppressed solar activity. The Bray-Holstadt cycle, running approximately 2,300 years, appears in cosmogenic isotope records and corresponds to what researchers call solar grand minima and maxima, extended periods of unusually low or high average activity. These longer cycles are real features of the solar record. Their physical basis is not fully understood, but they are not controversial in the way that planetary influence claims are. The danger in this landscape is twofold and cuts in opposite directions. On one side, legitimate uncertainty about long solar cycles and the limits of our understanding can be exploited to construct narratives that go well beyond what the data supports. The claim that the Sun operates on a 12,000-year catastrophic cycle, periodically novaing or producing extinction-level events, is not supported by the isotope record. The record shows Miyake events, which are serious, and grand minima and maxima, which affect climate and space weather rates, but nothing in the data suggests a 12,000-year catastrophic periodicity. That claim misinterprets the Holocene, a roughly 12,000-year warm period following the last glacial maximum, as evidence of a solar cycle rather than a climatic one. On the other side, dismissing all claims about solar behaviour that exceed the comfortable bounds of the instrumental record risks missing something genuinely important. The Miyake events themselves were, for a long time, not part of the mainstream conversation about solar risk. The researchers who took the isotope data seriously before the wider field caught up were not cranks. They were people reading a record that the field had not fully engaged with. The lesson is not that we should believe unconventional solar claims. The lesson is that the Sun's behaviour on long timescales is a legitimate scientific frontier, that our models are built on a short and incomplete observational record, and that the boundary between what is proven and what is simply assumed to be impossible is less well defined than institutional science communication typically conveys. Part 8. The Myth Machine, and what it tells us about real fear. When real science contains genuine gaps and genuine uncertainties, something moves into those gaps. Not always something accurate. Sometimes it is a constellation of interconnected claims that invoke real data, real discoveries, and real scientific terms, but assembles them into a picture that the actual evidence does not support. The solar catastrophe genre of fringe content is a useful case study in how this works, and also in why it works, which is the more interesting question. The most persistent alternative solar narrative involves a claim that the Sun periodically undergoes a micronova or some equivalent catastrophic discharge event on a cycle of approximately 12,000 years. The claim varies in its specifics depending on the source, but the common thread is that this supposed cycle is hidden from mainstream science, that ancient civilizations encoded warnings about it in monuments and myths, and that we are, at this moment, near the dangerous end of the current cycle. The first thing to say is that there is no peer-reviewed evidence for a 12,000-year solar catastrophe cycle. The cosmogenic isotope record, which is the actual scientific tool for reconstructing solar behavior on long timescales, does not show a recurring catastrophic signal at that periodicity. Miyake events appear in the record, but they are not distributed at 12,000-year intervals and show no sign of representing a fundamentally different solar state, rather than an extreme version of known solar particle events. The 12,000-year figure appears to derive primarily from a conflation of two unrelated things. First, the Holocene, the current warm interglacial period, began approximately 12,000 years ago at the end of the last ice age. Second, the Younger Dryas, a rapid cooling event that occurred around 12,900 years ago and ended abruptly, has attracted various impact and catastrophe hypotheses. Neither of these is a solar cycle. The Holocene is a climatic period defined by orbital and greenhouse gas conditions. The Younger Dryas is a terrestrial and atmospheric event whose cause is still debated, but for which the solar evidence is weak. What the Max Planck Institute's 2004 solar reconstruction using cosmogenic isotopes actually showed was that solar activity in the 20th century was at one of its highest levels in the past 8,000 to 11,000 years, a modern grand maximum. This is a real and scientifically interesting finding. It has been used in various contexts to argue for a coming solar grand minimum, since maximum activity periods tend to be followed by lower activity periods on the Gleisberg and Bray-Hallstatt cycles. But it says nothing about catastrophic periodic solar events, and it certainly does not support a 12,000-year disaster cycle. The reconstruction shows slow, modest fluctuations in average activity, not evidence of a periodic explosive event. Why do these narratives persist and propagate? The honest answer is that they are filling a genuine emotional need with inaccurate content. The underlying anxiety that drives interest in catastrophic solar narratives is not irrational. The sun genuinely is capable of producing events far beyond anything in our modern experience. The infrastructure of civilization genuinely is more vulnerable than most people realize. The mainstream scientific and government response to space weather risk genuinely is inadequate relative to the potential consequences. All of these things are true. The catastrophe narratives are, in a distorted way, pointing at real problems. They are just getting the details almost entirely wrong. The effect of this is harmful in a specific way. When someone investigates extreme solar risk and encounters the fringe content first, as frequently happens in online searches, they face a choice between two apparently opposed positions. The fringe narrative that says catastrophe is imminent and predictable and encoded in ancient knowledge, and the mainstream dismissal that sometimes seems to be dismissing the underlying risk, along with the fringe interpretation. Neither position is accurate. The fringe exaggerates and fabricates. The mainstream dismissal sometimes understates the real and serious risk that peer-reviewed science documents. Scientists who study Miyake events occasionally find themselves in the frustrating position of needing to assert that yes, the sun has produced extreme events far beyond anything in the modern record, and no, this does not confirm the 12,000-year disaster cycle, and also yes, the risk is real and serious and under address by policy, all at the same time, in a public communication environment that tends to prefer simpler stories. The one thing the catastrophe narrative gets right, unintentionally, is the basic emotional register. Taking the sun seriously, treating it as a system capable of producing surprises that our current models do not anticipate, maintaining genuine humility about the completeness of our understanding. These are appropriate responses to the evidence. They are just not the same as believing specific unfounded claims. Anxiety, properly calibrated and directed, leads to preparation. Anxiety misdirected by inaccurate framing leads to paralysis or dismissal. The actual risk is strange enough and serious enough that it does not need to be embellished. The tree rings already tell a more alarming story than any fringe narrative, because the tree rings are real. Part 9. The window, the warning, and the useless minutes. The warning system for space weather is a remarkable technical achievement that is, in the most important respects, not fit for purpose. This is not a criticism of the engineers and scientists who built and operate it. It is a structural feature of the physics that makes the problem, in its current form, essentially unsolvable by early warning alone. The most important piece of hardware in Earth's space weather defense network is a satellite called NOAA's Space Weather Follow-on at L1, or as WFO L1. It sits at the first Lagrange point between Earth and the Sun, approximately 1.5 million kilometers sunward. At that position, it measures the solar wind, including its speed, density, and magnetic field orientation in real time. When a CME passes by this satellite, scientists on Earth receive the data. They know the storm is coming. They begin alerting grid operators, satellite controllers, and aviation authorities. The problem is propagation time. At a typical CME speed of 500 to 1,000 kilometers per second, the distance from L1 to Earth takes between 15 minutes and an hour to traverse. For a fast CME, the kind associated with the most dangerous events, the warning time can be as short as 15 to 20 minutes. And here is the critical technical limitation that is almost never communicated clearly in public coverage. The magnetic field orientation of a CME, the single most important factor in determining how badly it will disturb Earth's magnetosphere, cannot be accurately determined until the CME passes the L1 satellite. The CME's magnetic field configuration is set by its internal structure, which can only be measured when the instruments physically encounter it. Why does the magnetic field orientation matter so much? A CME with a southward pointing magnetic field, described by the technical term -BZ, is far more geo-effective than one with a northward pointing field. A northward field tends to slide past Earth's magnetosphere without coupling strongly. A southward field couples efficiently, driving magnetic reconnection on the dayside magnetopores and injecting large amounts of energy into the magnetosphere. The difference between a moderate storm and a severe storm is often not how much plasma is in the CME, but which direction its magnetic field is pointing when it arrives. You cannot determine this from solar observations alone. You have to wait for the CME to arrive at L1, and by then you have 15 to 60 minutes before it hits Earth. During that window, what can realistically be done? Satellite operators can put spacecraft into safe mode, which protects some systems but not all. Grid operators can reduce the amount of power being transmitted through the longest transmission lines, reducing but not eliminating GIC risk. Aircraft over the poles can begin descending. None of these actions are sufficient to fully protect infrastructure from a major event. They are damage reduction measures that make a bad situation moderately less bad. The European Space Agency has been developing a mission called Vigil, designed to position a spacecraft at the fifth Lagrange point, L5, which sits 90 degrees behind Earth in its orbit around the Sun. From that location, a solar imager could observe CMEs as they leave the Sun's western hemisphere, before they rotate into Earth-facing position, providing days of warning that a potentially threatening region exists. This would not solve the magnetic field orientation problem, but it would give more time for preliminary preparations and extend the window in which grid operators can adjust system states. The Vigil mission represents genuine progress, but it is still under development as of 2026 and will not be providing operational data for several more years. In the meantime, the current L1 observation capability represents the operational state of the art for direct CME warning, with all its limitations. There is a deeper problem that the technical discussions sometimes obscure. Warning systems are only as useful as the response capacity that exists behind them. Even with 30 minutes of warning, a grid operator can only take actions that the physical infrastructure makes possible. If the transformers are not protected, the warning allows the operator to watch them fail with advance notice, rather than fail in surprise. True resilience requires not just better warning, but physically hardened infrastructure that can survive a severe event even with minimal warning time. And that hardening requires investment decisions that have not been made. The gap between the warning capability and the response capability is where the real risk lives. It is also where the most tractable interventions lie, because unlike the fundamental physics of CME propagation, the decision to invest in transformer protection or spare equipment stockpiles is a policy choice that does not require solving any unsolved scientific problems. Part 10. The trillion-dollar bet. We are all losing. There is a number that appears in the serious economic literature on space weather risk, and it is large enough to be genuinely difficult to hold in the mind. not in the way that astronomical distances are difficult to hold in the mind, where the scale is so remote it feels abstract and harmless. This number is difficult to hold in the mind because it is attached to something real, something that affects every person alive today, and because the response to it has been, in the most precise possible terms, almost nothing. The Lloyd's of London estimate of $2.6 trillion in potential losses from a major geomagnetic storm affecting the North American grid is not the upper bound of the damage scenario. It is a central estimate for a Carrington-class event, meaning an event roughly equivalent to the 1859 storm that knocked out telegraph infrastructure across 2 continents. More recent analyses, accounting for the increased interconnection and digitization of infrastructure since 2013 when that estimate was published, have produced numbers that are meaningfully higher. The world has become more dependent on electricity and digital systems in the intervening years, not less. The vulnerability has grown. The estimate has not been revised downward. For context, $2.6 trillion is approximately 10% of annual United States GDP. It is more than the entire economic output of France in a given year. It is a loss of a magnitude that has no modern precedent in peacetime. Natural disasters, financial crises, even the economic disruption of the COVID-19 pandemic, which was itself the largest peacetime economic shock in a century, produced losses that were serious and recoverable. A $2.6 trillion infrastructure loss, concentrated in the power and communication sectors, would not be recovered from quickly, because the thing that recovery depends on, functioning power infrastructure, is precisely what would be gone. And this estimate comes from an institution that is not known for catastrophism. Lloyd's of London is an insurance market. It exists to price risk accurately. Its analysts are actuaries who are professionally, legally, and commercially required to be conservative in their estimates, because overestimating losses costs money and underestimating them costs more. When an insurance market publishes a central estimate of $2.6 trillion in potential losses from a space weather event, it is not making a dramatic claim for public attention. It is doing its job. And its job, in this case, produced a number that should have triggered immediate and sustained policy response. It did not. The mitigation cost estimates tell a different and considerably more uncomfortable story. The primary technical interventions that engineers broadly agree would reduce grid vulnerability are not exotic or experimental. They are known, tested, deployable technologies. Neutral current blocking devices installed on transformer grounding circuits prevent the geomagnetically induced direct currents from saturating transformer cores. Strategic stockpiling of spare extra high voltage transformers ensures that failed units can be replaced within weeks rather than years. These 2 interventions, applied systematically across the highest risk portions of the North American grid, have been estimated to cost somewhere between $200 million and $400 million in total. Let me be precise about what that ratio means, because it is the kind of number that sounds like a misprint until you check it twice. The protection cost is somewhere between 1/10 and 1/40% of the potential loss. In the language of financial risk management, this is not a difficult investment to justify. A hedge with a potential return of several hundred to several thousand times the cost is not a marginal proposition. It is, by any rational framework for evaluating risk mitigation expenditure, one of the most favourable investments a government or regulatory body could make. Infrastructure economists who work on resilience planning struggle to identify comparable examples where the ratio of mitigation cost to avoided loss is this favourable, and yet, as of 2026, these protections have not been widely deployed. A minority of high-risk transformers in the North American grid have neutral current blocking devices installed. The minority is not a large one. There is no adequate strategic reserve of spare extra high-voltage transformers maintained anywhere in North America. Government programs to address both of these gaps exist, and they have been existing in various stages of planning and partial implementation for the better part of 2 decades. The gap between current protection levels and what the documented threat envelope actually warrants is not a small one that is being incrementally closed. It is a large one that is being incrementally discussed. The reasons for this gap are not, it must be said, mysterious. They are entirely ordinary. They are the standard mechanics of public policy and action, applied to a risk that has the particular misfortune of being low frequency, diffuse in its benefits, and mismatched in its timing with the rhythms of political decision-making. The threat is low frequency enough that it does not generate sustained political attention. a risk that might materialize this decade or might not materialize for another century, does not have the visceral urgency of a flood that has already happened or a wildfire currently visible on the horizon. Politicians and regulators respond to events and to organized constituencies. Extreme space weather has produced neither a recent catastrophic event in a developed country, nor an organized constituency of people whose livelihoods depend on grid hardening being funded. The engineers who understand the risk are not, as a group, effective political lobbyists. The communities that would be most harmed by a major grid failure do not know they are the communities most at risk. The benefits of protection are diffuse in a way that makes political advocacy structurally difficult. Grid resilience against a rare extreme event accrues to everyone in the affected region as an avoided loss, meaning nobody gets a check, nobody gets a ribbon-cutting ceremony, nobody gets to run a campaign advertisement about the catastrophe that was prevented because no catastrophe occurred. The political economy of invisible benefits is brutal. You cannot hold a press conference about the hospital that did not lose power, the water treatment plant that did not go offline, the supply chain that did not collapse, because none of those things happened. The costs of protection, meanwhile, are immediate, visible, and accountable. The $200 to $400 million investment appears in a budget. It gets scrutinized in an appropriations hearing. Someone has to defend it against other priorities, and the honest defense that we are spending this money to protect against something that has a perhaps 10 to 15% chance of occurring in the next decade and a near certainty of occurring at some point in the coming centuries is not a defense that wins budget battles against programs with immediate demonstrable constituencies. Utility companies operating in regulated environments face a version of the same problem. They are permitted to earn returns on capital investments through the rate-setting process. But those investments are typically justified by their contribution to serving current customers reliably. An investment in protecting against a rare extreme event imposes costs on current customers to protect future customers against a scenario that has never occurred in the utility's operating history. Regulators are not always willing to approve those costs, and utilities are not always motivated to push for approval. The international dimension adds further complexity to an already intractable situation. The countries with the greatest financial resources to invest in grid hardening are not necessarily the most geographically vulnerable to geomagnetic effects. Geomagnetic storms produce their most severe ground-level effects at higher latitudes, making Canada, the northern portions of the United States, Scandinavia, Iceland, and Russia more vulnerable than equatorial regions. But the supply chains for critical grid components, including the factories that manufacture extra-high voltage transformers, span the globe. A severe geomagnetic event that damaged grid infrastructure in high-latitude countries would have cascading effects on economic activity worldwide, including in countries whose own grids experience minimal direct damage. The incentive to free-ride on other countries' hardening investments, if those investments were ever made, is built into the structure of the problem. Some countries have made meaningful and genuine progress. The United Kingdom's National Risk Register formally lists space weather as one of the top-tier national risks, placing it in the same category as pandemic disease and major flooding. This classification has driven at least some investment in monitoring capability and emergency planning. Finland and Norway, with both high latitude exposure and long operational experience managing geomagnetic effects on power infrastructure, have invested more systematically in monitoring systems and some hardening measures than most comparable economies. The United States, through the Department of Energy and the Federal Energy Regulatory Commission, has produced technical guidelines and a limited number of regulatory mandates for space weather preparedness. Implementation of those mandates remains incomplete, and the mandates themselves fall short of what the documented risk level warrants. The most honest assessment of global preparedness does not come from policy advocates, insurance companies, or government agencies. It comes from the researchers who study the actual threat. When those researchers are asked directly whether current global infrastructure could survive a Miyake-class event without catastrophic disruption, the answer is consistent and unambiguous. No, not because such an event is necessarily imminent, but because nothing has been done at the scale required to prepare for it. The infrastructure that exists today was not designed with a Miyake-class event in mind. The protection standards that govern its operation were not written with a Miyake-class event in mind, and the political processes that would need to change this have not so far treated the risk as sufficiently urgent to act upon. at the required scale. The extraordinary quality of this situation is not its complexity, it is its clarity. Every person in the chain of decision-making, from transformer engineers to utility regulators to congressional appropriators to heads of government, can look at the same numbers and follow the same argument. The threat is documented, the mitigation is affordable, the action is technically feasible, the ratio of cost to avoided loss is almost absurdly favourable, and the action has not been taken. This is not ignorance. It is not a failure of analysis. It is something more structurally troubling, a collective and entirely rational seeming failure to act on information that is clearly available in the face of a risk that is understood, for reasons that have everything to do with the structure of incentives and essentially nothing to do with the quality of the evidence. Every day that passes without action is, in a narrow actuarial sense, a day on which the bet paid off. The sun was quiet. The grid survived. Nothing happened. And the lesson that most institutions draw from nothing happening is that nothing will happen. The sun does not care about that lesson. It is not running on our calendar. It is not waiting for the right policy window. It has its own timeline, written in physics rather than politics, and it has demonstrated in the chemical memory of trees that were alive before any of our institutions existed, that it is entirely capable of rewriting the terms of the conversation without notice, without warning, and without the faintest interest in whether we were ready. Part 11. The night. The sky glowed. In March 2026, something quietly remarkable happened over a large portion of the Northern Hemisphere, and like most of the genuinely important things our sun does, it was experienced by the majority of people who noticed it as nothing more than an unusually good opportunity for photographs. The spring equinox was approaching. Days and nights were equalizing across the planet, the familiar astronomical milestone that marks the moment Earth's axial tilt brings both hemispheres into symmetrical relationship with the sun. For most people, the equinox is a calendar event, the beginning of spring in the north, the beginning of autumn in the south, a date that appears on weather apps and gets mentioned in passing. For space weather scientists, it is something more specific and more consequential, a period of reliably enhanced vulnerability to geomagnetic disturbance, arriving twice a year with the punctuality of orbital mechanics, whether the infrastructure community is paying attention or not. A solar wind stream from a coronal hole arrived at Earth during that March window. Coronal holes are regions of the sun's surface where the magnetic field opens outward rather than looping back, allowing solar wind to escape into interplanetary space at higher speeds and with a different particle composition than the surrounding solar atmosphere produces. They are not dramatic events. They do not generate the sharp spike of an X-class flare or the CME imagery that makes it onto science news websites. They are quiet, persistent, and in the right geometric circumstances, remarkably effective at disturbing Earth's magnetosphere. This particular stream interacted with the magnetosphere at an angle that maximized its coupling efficiency. The result was a widespread aurora display visible across latitudes that do not normally see colored lights in the sky, and for several hours the KP index, the global planetary index that measures the intensity of geomagnetic disturbance on a scale from 0 to 9, climbed into the range that operational space weather forecasters watch with close attention. Grid operators in high-latitude regions ran through their monitoring protocols. Satellite operators put some spacecraft into protective orientations. And across a wide band of the Northern Hemisphere, people stepped outside, looked up, and reached for their phones. The equinox effect is one of the genuinely underappreciated features of space weather, absent from most public discussions of solar risk, and rarely mentioned in the coverage that follows major geomagnetic events. The mechanism involves the geometry of how Earth's magnetic dipole axis is oriented relative to the incoming solar wind at different times of year. During the equinoxes, this geometry creates conditions in which the same solar wind speed and the same particle density drive significantly stronger geomagnetic effects than it would produce during the solstice months. The physics centers on the efficiency of magnetic reconnection at the dayside magnetopause, the outer boundary of Earth's magnetic field on the sun-facing side, and how effectively solar wind energy is transferred into the magnetospheric system, depending on the angle of encounter. The statistical signature of this effect is clearly visible in the historical record of geomagnetic storms going back more than a century. Severe geomagnetic events are meaningfully overrepresented in March and September, relative to June and December. This is not a subtle trend that requires careful statistical analysis to detect. It is a robust pattern that appears consistently across different datasets and different methodologies. Twice a year, the geometry of Earth's orbit creates a window during which the Sun's output is more efficiently converted into geomagnetic disturbance. Twice a year, that window opens and closes without most people knowing it existed. Understanding why auroras look the way they do adds another layer to what these events are actually communicating. The coloured lights that people photograph and post are not decorative. They are a direct physical map of where energy is being deposited into Earth's upper atmosphere, and the colours are determined by the specific atoms involved and the altitude at which the collisions occur. Charged particles injected into the magnetosphere during a geomagnetic disturbance travel along magnetic field lines down toward the polar regions, colliding with oxygen and nitrogen atoms in the upper atmosphere and exciting those atoms to higher energy states. When the atoms return to their ground states, they release that energy as light. Oxygen atoms at approximately 100 kilometers altitude produce the green aurora that is the most commonly photographed colour, the ribbons and curtains that have become the visual signature of space weather events in popular culture. Oxygen at higher altitudes, where the atmosphere is thinner and the atomic collisions less frequent, produces red aurora, the deep crimson tones that appeared in the Florida photographs of May 2024, and that many people initially assumed were camera artifacts or processing errors because they had never seen them before. Nitrogen produces blue and purple tones, most visible at lower altitudes. The aurora is, in this sense, a spectrographic display painted across the sky in real time, a colour-coded readout of atmospheric chemistry under energetic bombardment. It is genuinely one of the more beautiful things that physics produces. It is also a diagnostic instrument that anyone with functioning eyes can read if they know what they are looking at. The auroras of May 2024 reached Florida and Hawaii and Jamaica because the geomagnetic storm was powerful enough to expand the auroral oval, the ring of continuous aurora that normally hovers over the polar regions, far enough toward the equator that it encompassed latitudes where aurora is essentially never observed under normal conditions. The KP index during that storm reached 9, the maximum value on the standard scale, and held there through multiple measurement periods. The equatorial boundary of the visible aurora descended to latitudes that have no living memory of the phenomenon, no recorded memory in the historical literature, and in some locations, no documented occurrence in roughly 5 centuries of written records. People photographed it. They posted it. The images were extraordinary. Phones captured colours that eyes struggled to process as real. The comment sections were uniformly celebratory, and simultaneously, in control rooms operated by power utilities and satellite companies across North America and Europe, engineers were monitoring readouts that told a parallel story. Geomagnetically induced currents flowing through transmission infrastructure, satellite orbits decaying faster than nominal due to atmospheric expansion from solar heating, high-frequency radio links degraded or unavailable across multiple frequency bands. The same event experienced as magic by one group of observers and as a technical emergency by another, unfolding simultaneously, with the two groups having almost no overlap and essentially no shared conversation about what was actually happening. The March 2026 event was considerably more modest. A KP 6 to 7 event occupies the middle of the upper range of the scale, a strong storm rather than a severe or extreme one. It was the kind of event that occurs several times per solar cycle, that professionals monitor carefully and manage without crisis, and that most of the public does not hear about because the disruptions it produces are real but contained. Grid operators ran their protocols, a small number of satellite operators adjusted spacecraft attitudes. Several high-frequency radio communication circuits experienced degraded performance for a period of hours. And then the solar wind stream passed, the KP index descended, the aurora retreated to its normal polar home, and the news cycle moved on to other things, as it invariably does when a space weather event fails to produce a dramatic visible consequence that can be described in a headline. But there is something worth sitting with in the ordinariness of that March event, in the way it arrived, produced its effects, and departed without leaving a mark on public consciousness. The equinox geometry that amplified its impact will return in September, and in the following March, and in every equinox for as long as Earth continues its current orbital configuration, which is to say, for a time frame that makes the entire history of human civilization look like a rounding error. The solar activity that drives these events is currently elevated above the predictions that were made for this solar cycle, running in a regime that has already produced the strongest geomagnetic storm in 2 decades, and that continues to generate significant flare and CME activity. The infrastructure that would be stressed by an extreme event arriving during an equinox window has not been hardened against that combined threat. These 3 facts, the recurring seasonal vulnerability, the elevated solar activity, and the unprotected infrastructure, do not add up to a prediction. They add up to a condition. A persistent structural condition in which the probability of a bad outcome is higher than it needs to be, and higher than most people who depend on that infrastructure understand it to be. The aurora that people photograph during these events is doing something that no public communication campaign has managed to do. It is making the invisible visible. The geomagnetic disturbance that is simultaneously flowing through ground-level infrastructure has no colour, no visual expression, no photogenic quality that anyone can share on social media. It exists in the thermal readings of transformer cores and the telemetry of satellites and the error logs of communication systems. The aurora is the only part of the space weather event that most people ever perceive directly, and it is perceived almost universally as beautiful rather than as diagnostic. There is nothing wrong with finding it beautiful. The physics that produces it is genuinely remarkable. The collision of charged particles with atmospheric atoms at the edge of space, the quantum mechanics of atomic emission, the grand-scale geometry of planetary magnetic fields bending the solar wind around a small rocky world, all of that is worthy of wonder. But standing under those lights and thinking only about their beauty is a little like standing on a beach, watching the water recede dramatically from the shoreline and thinking, what a lovely low tide. The beauty is real, the water is still going somewhere, and what follows a receding tide on a coastline with no warning system is not something that the people on the beach get to appreciate at a comfortable distance. The lights in the sky are telling us something. They always have been. The question has never been whether the message is there. It has always been whether anyone is reading it. Part 12. The Mirror Proposal and what we risk by rearranging the sky. Somewhere in the overlap between climate policy and astronomical hubris, someone proposed putting giant mirrors in space. Not metaphorical mirrors, not modest reflectors, not the kind of modest solar panel arrays that pepper rooftops and highway medians. Kilometre-scale orbital structures designed to redirect sunlight and either illuminate parts of Earth at night or shade portions of the planet from direct solar radiation as a deliberate climate intervention. The proposal is serious enough to have been published in peer-reviewed journals, discussed in policy circles, and considered by engineers who are not in the habit of entertaining ideas that have no physical basis. It is also, from the perspective of anyone who has spent time studying solar variability and the documented history of what the sun can do without any human assistance, a fascinating example of attempting to solve one problem while potentially creating several others that are considerably harder to reverse. The concept of space-based solar shading comes in several distinct forms, and it is worth understanding each of them on its own terms before evaluating the concerns they raise. Some proposals involve deploying a large quantity of reflective material at the first Lagrange point, the gravitationally stable position between Earth and the Sun, approximately 1.5 million kilometers sunward, to reduce the total solar irradiance reaching Earth, and thereby partially counteract the warming produced by accumulated greenhouse gases. The physics of this approach is straightforward in principle. Less sunlight reaching Earth means less energy absorbed, means less warming. The engineering of deploying enough material at L1 to produce a measurable climate effect is not straightforward at all, but it is not forbidden by any known physical law. Other proposals take a different form. Orbital mirrors in low or medium Earth orbit, positioned and angled to reflect sunlight onto agricultural regions during winter months, could extend growing seasons in high-latitude countries where food security is constrained by limited daylight. Some proposals envision mirrors that could illuminate cities at night, reducing the need for ground-based artificial lighting. These applications are more modest in scale than the L1 shading concept, and their climate effects would be localized rather than global. But they represent the same basic impulse: the recognition that the amount of solar energy reaching any particular part of Earth's surface is, at least in principle, an engineering variable rather than a fixed parameter. These ideas are not obviously insane. That is worth saying directly, because the instinct to dismiss them is understandable, but not entirely fair. The engineering challenges are enormous. The cost of deploying kilometre-scale structures to L1 would be measured in trillions of dollars, making it one of the most expensive engineering projects ever contemplated. The governance challenges are perhaps even more daunting than the engineering ones, because any intervention that changes the global distribution of solar energy affects every country on Earth, including countries that had no voice in the decision to deploy it. A space mirror that reduces solar irradiance over one region while increasing it over another is not a neutral technology. It is a geopolitical instrument of extraordinary consequence. But the motivation behind these proposals is genuine and serious. The pace of global warming, the demonstrated difficulty of achieving sufficient emissions reductions through international agreement, and the accelerating timeline of climate impacts have driven serious researchers to consider options that would have seemed like science fiction a generation ago. Solar geoengineering is not a fringe idea. It is a contested but legitimate area of climate science research, and the people working on it are grappling honestly with its risks and limitations. The question is not whether their concerns about climate change are valid. They are. The question is whether space mirror proposals adequately account for the full range of systems they would be intervening in. The astronomical community's concerns are the most publicly visible objection, and they centre on something concrete and irreversible. The night sky, as it exists in the absence of artificial light, is an observational resource that cannot be reconstructed once it is gone. It has informed human navigation, agriculture, religion, mythology, and scientific understanding for the entire duration of our species' existence. It is the medium through which essentially all of our knowledge about the universe beyond Earth has been acquired. The degradation of this resource by artificial light pollution is already a serious and worsening problem. Ground-based observatories that were built in rural darkness a century ago now operate under skies that are measurably brighter than they were at construction. The Starlink satellite constellation operated by SpaceX has generated sustained and serious concern among professional astronomers about the streaks of reflected light that large satellite arrays leave across long exposure images, interfering with surveys that require dark, uncontaminated fields. Space mirrors would not add a few hundred bright streaks to the night sky. Depending on their scale and orbital configuration, they could fundamentally alter the optical environment of near-Earth space in ways that make ground-based optical astronomy in certain wavelength ranges effectively impossible. A kilometre-scale reflector in low Earth orbit would be, at certain phases, one of the brightest objects in the night sky. A fleet of such reflectors sufficient to produce a meaningful climate effect would be visible continuously from any point on Earth's surface. The night sky that human beings have looked at for 300,000 years would be gone, replaced by something that is more convenient for agriculture and less useful for understanding the universe. This is a real loss, and it deserves to be weighed seriously. But from the space weather perspective, there is a different set of concerns that receives considerably less public attention, and that connects directly to everything documented in the solar risk literature. The fundamental problem is not aesthetic, and it is not about the rights of astronomers to a dark sky, legitimate as those concerns are. The fundamental problem is that we do not understand the sun well enough to be confidently manipulating our relationship with it at a civilization scale, at this moment, with our current level of knowledge. The solar variability that produces Miyake events, that drives the unpredicted intensity of solar cycle 25, that generates the geomagnetic storms that came within inches of causing major grid failures in May 2024, is a system whose behaviour on long time scales we are still reconstructing through indirect isotopic proxies, because our direct observational record is far too short to characterise its full range of behaviour. We know the Sun has produced events 500 times more energetic than anything in the modern record. We do not know when the next such event will occur. We do not know what precursor signals, if any, distinguish an ordinary solar maximum from one that is about to produce a Miyake-class particle storm. We are, in the most honest assessment of our epistemic position, operating with a partial map in a territory whose most dangerous features have not been visited in recorded history. Into that acknowledged uncertainty, space mirror proposals introduce a new and non-trivial variable. A large-scale deployment of reflective material at L1, precisely the location where our most critical space weather monitoring assets are positioned, could interfere with the observational infrastructure that provides the already inadequate warning time for incoming CMEs. The SWFOL-1 satellite, which measures the solar wind and magnetic field orientation of approaching plasma clouds, operates at L1 because that position provides the earliest possible detection of material heading toward Earth. Introducing a field of reflective debris or large structural elements into the same orbital region is not obviously compatible with maintaining clear observational geometry for space weather instruments. The engineers designing the mirror deployment would be optimizing for solar irradiance management. The space weather monitoring community would be watching their warning system degrade. Beyond the observational interference, space mirror systems introduce failure modes into an already inadequately protected infrastructure environment. A large orbital structure that is struck by a CME associated energetic particle event, or that experiences an anomalous charging event during a geomagnetic storm, could produce debris, could change orbital configuration, or could interact with the ionosphere in ways that the deployment models did not anticipate. These are not hypothetical concerns invented to obstruct climate intervention. They are standard considerations in the space environment engineering literature, applied to a class of object that has never been deployed at the proposed scale. There is something almost poetic in a quietly alarming way about the shape of this situation. Humanity, confronting the consequences of one large-scale inadvertent intervention in a global system, specifically the accumulation of greenhouse gases in the atmosphere as an unintended byproduct of industrialization, is now contemplating a deliberate large-scale intervention in another global system as the remedy. The first intervention was not designed. It was the aggregate result of billions of individual decisions made without knowledge of or intention toward the global consequences. The second intervention would be intentional, designed by serious engineers with the best available models and the most sincere desire to help. The asymmetry that should give everyone pause is temporal. The first intervention, the greenhouse gas accumulation, revealed its consequences over decades. The warming signal emerged gradually enough that there was time, however insufficiently used, to observe it, study it, debate it, and attempt to respond. The feedback was slow enough to be measured before it became irreversible. If something goes wrong with a large-scale space intervention in a moment of extreme solar activity, the consequences would not arrive on a decadal timescale. They would not provide decades for observation and response. A severe geomagnetic storm interacting with an inadequately modelled large orbital structure could produce consequences in the electrical and communications infrastructure of the affected hemisphere within minutes of the storm's arrival. The warning time for the interaction would be measured in the same 15 to 60-minute window that applies to any fast CME. And the failure mode would be operating in a system that had been deliberately modified in ways that the space weather risk models had not fully characterized. This is not an argument against taking climate change seriously. It is not an argument that solar geoengineering should never be studied or considered. It is a much simpler argument that a civilization which has not yet protected its power grid against a solar storm risk that mainstream science fully confirms, which has not stockpiled the transformer components needed to recover from a Carrington-class event, and which cannot predict its own star's behaviour well enough to have anticipated the intensity of the current solar cycle, should think very carefully before adding new variables to the solar terrestrial system in the name of solving a different problem. We are not in a position of comprehensive understanding looking to apply our knowledge wisely. We are in a position of partial understanding, managing known gaps, attempting to read a star whose full behavioural range is encoded in tree rings and ice cores rather than instruments. The hubris is not in wanting to solve climate change. The hubris is in assuming that we understand enough about the system we are modifying to be confident about what we are not accounting for. The Sun has been operating on its own terms for 4.6 billion years. It will continue to do so regardless of what we put between it and us. The question is not whether we can change our relationship with it. The question is whether we understand that relationship well enough to change it deliberately without making the parts we have already failed to address considerably worse. Part 13. The visitor with methanol on its breath. The universe occasionally sends us visitors, and they carry information from places we have never been and cannot visit, encoded in chemistry that formed billions of years ago around stars we can barely resolve as points of light. There is something almost implausible about the fact that objects from other stellar systems occasionally pass through our own, that the gravitational geometry of the galaxy allows a comet born around a distant star to swing through our neighbourhood, brush past our sun, and continue outward into interstellar space carrying the molecular signature of its origins. And yet this is not a theoretical possibility. It is something that has now been observed multiple times, and each observation has added something to our understanding of the universe that we could not have obtained any other way. In recent years, astronomers have identified a small but growing number of objects passing through the solar system on hyperbolic trajectories, meaning paths that are not closed orbits but open curves, arriving from interstellar space, bending around the sun under gravity, and departing again on a trajectory that will take them back out of the solar system and eventually into the spaces between stars. The defining characteristic of these objects is their speed. They are moving too fast to be gravitationally bound to the sun, which means they did not form here. They came from somewhere else, and they are passing through on their way to somewhere else again. The first confirmed interstellar visitor was the object now designated Oumuamua, detected in October 2017 by the Pan-STARRS telescope in Hawaii. It was already departing the inner solar system when it was found, which meant the observational window was short and the data collected was limited. What the data showed was puzzling enough that the scientific debate about Oumuamua's nature has not fully resolved. It appeared to be highly elongated, possibly cigar-shaped, or possibly flat like a pancake, depending on which model was applied to the light curve data. It showed an unexpected acceleration away from the sun that could not be explained by gravitational forces alone. Various explanations were proposed: outgassing of volatiles, radiation pressure on an unusually thin object, and others that attracted more public attention than scientific consensus. Oumuamua remains genuinely mysterious, and that mystery is itself informative. The first interstellar visitor we ever identified did not fit neatly into any category our solar system experience had prepared us for. The second confirmed interstellar visitor was considerably more cooperative. Borisov, formerly designated 2I/Borisov and discovered in August 2019 by amateur astronomer Gennady Borisov, was unambiguously a comet. It had a visible coma, meaning an envelope of gas and dust evaporating from its nucleus under solar heating, and a tail. It behaved like a comet in every observable respect. Spectroscopic analysis revealed the presence of familiar cometary molecules, water, carbon monoxide, and other species that are common in comets, originating within our own solar system. Borisov was, in the most meaningful chemical sense, unremarkable. It looked like a comet from our solar system. This was actually a significant finding. It suggested that the basic chemistry of comet formation, the ices and organics that condense in the cold outer regions of a protoplanetary disk, may be relatively universal across stellar systems. The building blocks appear in similar proportions around at least some other stars. The object designated 3I/Atlas, detected more recently, added a new chapter to this emerging field of interstellar object astronomy. The detection of elevated methanol content in this object's spectral signature drew particular scientific attention, because methanol is not among the simplest cometary molecules. It is a more complex organic compound whose presence in significant quantities tells a specific story about the thermal and chemical history of the material from which the comet formed. Methanol forms in the icy mantles of dust grains in cold, molecular cloud environments through the hydrogenation of carbon monoxide under conditions of very low temperature and high radiation exposure. Its presence in an interstellar comet suggests that the protoplanetary disk around its parent star included regions cold enough and chemically active enough to produce complex organic ice chemistry, conditions broadly similar to those that prevailed in the outer regions of our own solar system during its formation. The scientific significance of this extends in several directions simultaneously. It bears on questions of how common planetary systems like ours are throughout the galaxy, since the chemical conditions that produce methanol-rich comets are associated with the same disk conditions that produce the outer planet architecture of systems like our own. It bears on questions of how widely distributed the organic chemical precursors to life might be, since methanol is a molecule that participates in the chemistry that produces more complex organic compounds, including amino acid precursors under the right conditions. And it bears, in a way that is less immediately obvious but more relevant to our solar narrative, on questions about the stellar environments that these objects came from and what those environments can teach us about the range of what stars do. Because here is the connection that the interstellar object literature tends not to foreground, and that becomes significant when you have been thinking carefully about Miyake events and the documented range of solar behaviour. The space weather environment around a star is not a fixed or universal thing. It is determined by that star's mass, age, rotation rate, and magnetic field configuration, all of which evolve over the star's lifetime, and all of which vary substantially from star to star, even among objects of similar mass and spectral type. The Sun is a G-type main sequence star of middle age, rotating relatively slowly for its class, with a magnetic activity level that is, by the standards of the broader stellar population, on the quieter end of the distribution. This relative quietness is one of the reasons Earth has maintained a stable enough environment for complex life to develop over billions of years. But quiet is not the same as inactive, and the comparison with other Sun-like stars is instructive in a way that should recalibrate our intuitions about what our own star is capable of. Data from the Kepler Space Telescope, which monitored the brightness of hundreds of thousands of stars continuously for years, has revealed that super flares, meaning flares hundreds to thousands of times more energetic than the largest solar flares in the modern instrumental record, occur regularly on stars that are in many respects similar to the Sun. The frequency of these events decreases as stars age and their rotation slows, because magnetic activity is driven partly by rotation rate, and older stars rotate more slowly. The Sun, at 4.6 billion years old, rotates slowly enough that its superflare rate is very low by the standards of the broader G-type star population. Very low is not zero, and the tree ring record with its documented Miyake events at 775 CE and 993 CE, and the prehistoric spike 14,300 years ago, is the empirical evidence that very low frequency extreme events have occurred in our own system. The stellar superflare data from Kepler provides the broader context. The Sun is operating in a regime where extreme events are rare, constrained by its age and rotation rate, but not physically prohibited. The physics that produces superflares on younger, faster rotating Sun-like stars is the same physics that operates in our own Sun. It is operating more quietly here, most of the time. But most of the time is not all of the time, and the isotope record is the proof. An interstellar comet, like 3I/Atlas, spent an almost incomprehensible amount of time in transit between its home system and ours. The distances between stars in our part of the galaxy are measured in light years, and objects moving at typical interstellar velocities of tens of kilometers per second take tens of millions of years to cross them. During the entire duration of recorded human history, a period of perhaps 5 to 10,000 years depending on how you count it, this object was somewhere in the cold dark between stars, experiencing nothing more energetic than the diffuse cosmic ray background of interstellar space. During its home system's history, which stretched over billions of years before its ejection from that system, its parent star may have produced dozens of Miyake-class events, or none, or something in between, entirely depending on that star's magnetic character and evolutionary history. The comet carries no record of this. Its methanol content is a memory of its birth, not of its star's subsequent behaviour, but its arrival in our system is a prompt to think about the diversity of stellar environments in a way that has direct bearing on how we understand our own. The perspective shift that interstellar objects offer is both spatial and temporal, and both dimensions are humbling in similar ways. Spatially, the detection of chemically familiar material arriving from another stellar system is a reminder that our solar system is not an isolated experiment. It is one instance of a process that occurs throughout the galaxy, producing planetary systems of varying architectures around stars of varying temperaments in environments whose space weather histories are as varied as the stars themselves. The chemistry may be broadly similar, the stellar behaviour is not. Temporally, the challenge is even more fundamental. On the scale of galactic time, the Sun's behaviour over the past 2 centuries of direct human observation is not even a rounding error. It is a single data point in a distribution that spans billions of years. The tree ring record, which extends our view to roughly 14,000 years, is a modest improvement on that pixel, but it remains vanishingly short relative to the timescales over which stellar magnetic behaviour evolves. Grand minima and maxima come and go, and the full range of extreme events accumulates. We are trying to characterize the behavior of a 4.6 billion-year-old star using a sample window that represents approximately 3 millionths of its lifetime. The real record of what our Sun has done across its full history is written in ways that we are only beginning to develop the tools to read. Some of it is preserved in cosmogenic isotopes in ice cores and tree rings, the archive we have been exploring throughout this narrative. Some of it may be recoverable from lunar soil samples, which preserve a record of energetic particle bombardment going back billions of years, and which have barely been analysed for this purpose. Some of it may be accessible through the geological record of atmospheric chemistry changes associated with extreme particle events. These archives exist. They have not been fully opened. What the interstellar visitor with methanol on its breath reminds us, in its quiet chemical way, is that every star has a history that its planets live inside. The history shapes the environment shapes what survives. And the history of our own star, read through the limited but expanding archive of isotopic proxies and stellar comparisons, is telling us something that we have not yet fully integrated into how we think about the civilization we have built in its light. Part 14, When Stars Collide and What It Teaches Us About Scale. There is a category of astronomical event that makes even Miyake events seem local and modest, that makes the entire history of human civilization seem like a brief flicker of light in a universe that operates on timescales and energy scales so extreme that our most powerful instruments only recently became sensitive enough to detect them at all. The merger of two neutron stars is not an event that fits comfortably into the human imagination. It requires a different kind of mental scaling, the kind that starts with the most extreme things we know about, and then asks you to go considerably further. A neutron star is what remains after a massive star, somewhere between 8 and 20 times the mass of the Sun, exhausts its nuclear fuel and collapses. The outer layers are expelled in a supernova explosion. The core is compressed by gravity to a density that has no analogue in ordinary experience. A neutron star typically contains more mass than the Sun packed into a sphere roughly 20 kilometers across, approximately the size of a mid-sized city. At that density, the material is not composed of atoms in any conventional sense. The electrons and protons that make up ordinary atomic matter have been forced together under the crushing gravitational pressure to form neutrons, packed together in a state that is essentially a single enormous atomic nucleus. A teaspoon of neutron star material would weigh approximately 1 billion tons on Earth's surface. The surface gravity is approximately 200 billion times Earth's. When two of these objects orbit each other in a binary system, they lose energy through the emission of gravitational waves, the ripples in space-time that Einstein's general theory of relativity predicted, and that the LIGO and Virgo gravitational wave detectors confirmed in spectacular fashion, beginning with the first direct detection in 2015. As the binary system loses energy to gravitational wave emission, the two neutron stars spiral inward toward each other over timescales that can range from millions to billions of years, depending on the initial orbital parameters. The spiral accelerates as the separation decreases. Eventually, the two objects make contact and merge in a collision that lasts milliseconds and releases an amount of energy that is, by any human measure, incomprehensible. Each of these collisions releases more energy in those few milliseconds than the Sun will radiate across its entire 10 billion year main sequence lifetime. The energy is released in multiple forms simultaneously. Gravitational waves carry away a significant fraction of the total energy budget, as space-time itself ripples outward from the merger site at the speed of light. A relativistic jet of material is launched along the rotation axis of the merged object, producing a short gamma ray burst, a brief but intensely bright flash of gamma radiation that can be detected across billions of light-years of space. The merger also produces a slower-moving outflow of neutron-rich material called a kilonova, in which the rapid neutron capture process, the R process, forges heavy elements that cannot be produced in any other known astrophysical environment. Gold, platinum, uranium, and most of the other elements heavier than iron that exist in the universe were created in events like these, distributed through space by the kilonova outflow, eventually incorporated into new generations of stars and planets. The gold in any piece of jewelry you own was forged in a neutron star merger billions of years ago. The first direct observation of a neutron star merger in gravitational waves, combined with electromagnetic observations across multiple wavelengths, occurred on August 17, 2017, in an E-event designated GW170817. It was one of the most scientifically productive astronomical observations in history. The gravitational wave signal was detected by LIGO and Virgo. 2 seconds later, a short gamma-ray burst was detected by the Fermi and Integral space telescopes. In the hours and days that followed, observatories around the world and in space detected the kilonova afterglow, watching in real time as the merger debris expanded and cooled, and the spectroscopic signatures of newly synthesized heavy elements appeared in the data. It was, for astronomers who had spent careers preparing for exactly this kind of multi-messenger observation, something close to a professional culmination. The galaxy in which GW170817 occurred is NGC 4993, located approximately 130 million light-years from Earth. At that distance, the gamma-ray burst associated with the merger posed no threat to anything in our cosmic neighbourhood. The energy that reached Earth was detectable only by sensitive space-based gamma-ray instruments, arriving as a brief pulse of high-energy photons that carried information rather than hazard. But the same event occurring within a few thousand light-years of Earth would be a different matter entirely. A short gamma-ray burst from a neutron star merger at close range, particularly one whose jet happened to be aimed in Earth's direction, would deliver a radiation dose to the upper atmosphere capable of triggering significant ozone depletion on the illuminated hemisphere, with consequences for surface ultraviolet exposure that could persist for years. Some researchers have proposed that mass extinction events in Earth's geological past may have been associated with nearby gamma-ray bursts, though the evidence for specific events remains circumstantial. The connection to our solar story is one of scale and calibration, and it operates in a direction that is both reassuring and uncomfortable simultaneously. When we consider the risk from solar events, from Carrington-class CMEs and Miyake-class particle storms, we are operating within a threat envelope defined by phenomena that occur within our own star system, at distances of 1 astronomical unit or less. The Miyake events that the tree rings document are local in every cosmic sense. They are the Sun doing something unusual within its own behavioural range, not the universe deploying one of its genuinely catastrophic mechanisms. They are, in the grand hierarchy of astrophysical hazards, a relatively approachable problem, and yet they represent a level of threat that our most advanced civilization, with all its engineering capability and scientific knowledge, has not seen fit to adequately prepare for. This is the contrast that the neutron star merger literature makes vivid in a useful way. The events that occupy the full cosmic danger spectrum range from the locally manageable Miyake events and Carrington-class storms that are serious but survivable, with appropriate preparation, through intermediate categories like nearby supernovae, which would need to occur within perhaps a few hundred light-years to cause serious biological damage, and for which there are no known candidates in our immediate neighbourhood at present, to the cosmologically spectacular and currently irrelevant, the distant neutron star mergers whose gravitational waves we can detect but whose direct effects cannot reach us. Our position on this spectrum is genuinely fortunate. The most serious threats we face from the cosmos are ones that civilization, with political will and sustained engineering effort, could substantially mitigate. We're not in the position of a civilization facing an extinction-level threat from a source beyond any possible intervention. We are in the considerably more manageable and considerably more embarrassing position of facing a known and documented threat from our own star that we have chosen not to prepare for. The high-energy astrophysics illuminated by neutron star merger research also contributes to our understanding of the physical mechanisms that drive the solar events we have been discussing throughout this narrative. This is not an obvious connection, but it is a real one. The particle acceleration processes that produce the relativistic jets of short gamma-ray bursts, the magnetic reconnection and shock acceleration physics that operate in the extreme environment of a neutron star merger, involve the same fundamental electromagnetic and plasma physics that drives particle acceleration in solar flares and in the coronal shocks associated with fast CMEs. The scales are different by many orders of magnitude. The energy budgets are incomparably larger in the neutron star case. But the underlying physics, the way magnetic fields store and release energy, the way shock fronts accelerate particles to relativistic speeds, the way plasma instabilities drive explosive energy release, is continuous across these different astrophysical contexts. Studying the most extreme examples of these processes in neutron star mergers and in the relativistic jets of active galactic nuclei and gamma-ray bursts refines the theoretical frameworks that physicists apply to more modest versions of the same phenomena in solar physics. When theorists try to understand why some solar CMEs produce Miyake-class particle acceleration and others do not, the models they use draw on physics that has been tested and calibrated against observations of more extreme astrophysical accelerators. The neutron star merger that LIGO detected in 2017 contributed, in an indirect but traceable way, to the theoretical toolkit that solar physicists use to model the events that tree rings record. There is a long perspective available here, and it is worth occupying for a moment before returning to the immediate and practical concerns that have dominated this narrative. In the long perspective of astrophysics, the Sun is a middle-aged star in the stable, hydrogen-burning phase of its evolution, doing exactly what middle-aged G-type stars do, which is to say, producing energy through nuclear fusion at a rate that has been approximately constant for the past several billion years and will remain approximately constant for the next several billion. It formed from a molecular cloud that contained the heavy elements forged in previous generations of stars, including neutron star mergers that occurred before our solar system existed. It will continue its stable evolution for roughly another 5 billion years before the hydrogen in its core is exhausted, at which point it will expand into a red giant, engulf the inner planets, and eventually shed its outer layers as a planetary nebula, leaving behind a white dwarf. On that timescale, Miyake events are not catastrophes. They are routine fluctuations in the magnetic behaviour of a star going about its ordinary business. The tree ring record of extreme particle storms is, in the stellar autobiography, a minor footnote. On the human timescale, they are something else entirely. They are civilizational threats. They are events capable of disrupting the infrastructure that keeps several billion people alive, that took centuries to build, and that in many of its most critical components cannot be replaced quickly enough to prevent serious humanitarian consequences if it fails. The universe does not make this distinction. It does not organize its hazards by their relevance to the concerns of a particular species on a particular planet around a particular star. It operates according to physics, which is indifferent to what we have built and what we depend on and what we have failed to protect. The calibration, therefore, is our responsibility and ours alone. The neutron star mergers are happening in distant galaxies, forging gold and platinum and sending gravitational waves across the cosmos, entirely beyond our influence and mostly beyond our concern. The solar events are happening in our own backyard, driven by a star we have been watching for a century and a half, recorded in the archives of ancient trees, documented in the peer-reviewed literature, assessed by insurance actuaries and grid engineers and space weather scientists who are in broad agreement about both the risk and the remedy. We have the information, we have the technology, we have the resources. The distance between what we know and what we have done about it is not a scientific distance. It is a human one, and unlike the distance to a neutron star merger, it is a distance we are entirely capable of closing. Part 15, Standing Under the Shadow. There is something that happens during a total solar eclipse that no description quite captures. The light changes in a way that feels wrong before you understand why. Animals behave strangely, the temperature drops, and then the moon slides precisely into alignment with the sun, and for a few minutes you can see what is normally hidden by the overwhelming brightness of the solar disk, the corona, the sun's outer atmosphere, stretching out in delicate white threads and loops that look exactly like what they are, the source of everything we have been discussing. In 2026 there are significant eclipses to anticipate. A total lunar eclipse offers a different but complementary experience. The Earth casting its shadow on the Moon, a visible reminder of the three-body geometry that governs our immediate cosmic environment. And an upcoming total solar eclipse track across parts of the world will, for a few brief minutes, expose the corona to naked eye view for people standing in the path of totality. The corona is not just a spectacle, it is the source. The CMEs, the solar wind, the energetic particles, they all originate in or travel through the corona before they reach us. The complex magnetic structures visible in the corona during eclipses and in spacecraft imagery during the rest of the year are the physical expression of the processes that drive space weather. Watching the corona during an eclipse with knowledge of what it can produce is a different experience than watching it as simple beauty. We began this story on an evening in May 2024, when people in Florida looked up at auroras with wonder and took photographs for social media. That sense of wonder is real and legitimate. The lights were genuinely extraordinary. The fact that they were also a symptom of a geomagnetic storm that came close to causing infrastructure failures does not diminish their beauty. It adds weight to it. The thing about standing under the sky and looking up is that it is the same action whether you understand what you're looking at or not. The aurora over Florida was beautiful to everyone who saw it. It was alarming, in a measured and professional way, to a much smaller number of people who understood what was producing it. The difference between those two experiences is not a matter of the sky being different. It is a matter of what you carry with you when you look. The tree rings in 1,000-year-old oak samples carry a chemical record of a particle storm that swept over Earth in the year 775. Nobody who was alive that year had instruments capable of detecting what was happening. They may have seen unusual aurora. They may have noticed nothing at all. The event was recorded without any human observer understanding it, in the biochemistry of trees that were simply growing, absorbing carbon from the air, writing their annual rings in silence. We are in a different position. We have the instruments, we have the isotope data, we have the engineering knowledge to protect critical infrastructure against the most probable, severe events. We have the modelling capability to understand what we do not know as well as what we do. We're not helpless. We're not in the situation of those 7th century witnesses without tools or context. We are in the considerably more complicated situation of having excellent tools, reasonable context, and a consistent failure to act on the information they provide. The next Miyake event will not care whether we were prepared. It will not care about solar cycle predictions or policy cycles or budget negotiations or the political difficulty of long-term infrastructure investment. It will arrive, as all previous ones did, on its own schedule, recorded in the tree rings of whatever forests are still standing, and in whatever isotopic archives the future scientists who study it will depend upon. Whether it finds a civilization that hardened its grid and protected its critical systems, or one that kept filing the problem away as theoretical, is not determined by the sun. It is determined by us, in the years between the last warning and the next event, during which the sky's mostly quiet, the aurora stays near the poles where it belongs, and everything feels fine. The question is whether fine is the same as safe. The tree rings say it is not. The question is whether anyone is listening.